This is 14E, last exercise. Okay, so we're going to start off with question 1. Okay, a rod of length 2L and mass M is free to oscillate about a horizontal axis perpendicular to the length of the rod. Through a point which is distance x from the midpoint of the rod, it performs small oscillations. Find the value for which the periodic time is a minimum. Okay, so what we're going to do is we're going to get our rod. Draw the rod. Okay. So draw the rod here. Okay, it's length 2L. So 2L in length. And it oscillates about a horizontal axis perpendicular to the length of the rod through a point which is distance x from the midpoint of the rod. So call this the midpoint of the rod. And we're going to label this here, we're going to label its rotational axis O, because we don't actually know in this case if it's actually at the end of the rod or not. We actually don't know, so that's part of the problem here. Okay, so it's going dead center, as in the plane of oscillations going into the page. So it's sort of it's rotating like this, okay, but the problem is it's not rotating from the back end. There's going to be a little piece here as well that's rotating around as well. Okay, so it's not the standard one. Okay, so now that we have that determined, okay, what we're going to do is IC. Okay, now IC equals a third ml squared. That is when it's rotating perpendicular to its center. That's going straight through the center. So this theory here means it's going straight through its center. Okay, and what we're going to use the parallel axis theorem to get it to here. Okay, so it's a distance x from C. Okay, so now what we can use the parallel axis theorem to get its rotation around O, and its rotation around O is going to be IC plus MD squared. And what we're going to get there is we're going to get IO equals a third ML squared plus MX squared. Now what you can do there is you can multiply the top and bottom by 3, and then you can just take out a third M just to give it a nice round figure. So third M into L squared plus 3x squared. Okay, now the periodic time equals 2 pi the square root of inertia all over mgh. Okay, so if we substitute in our formula there, what we just got, it's going to be 2 pi times m L squared plus x squared, or sorry, 3x squared, be careful of that, 3x squared. Now the 3 goes on the bottom because it's a fraction, and it's just going to multiply in by the 3mg. Okay, so the 3 is going to appear on the bottom, m is going to be here, g is going to be here. Now remember what h is. H is the line of action compared to the center of gravity. The line of action is going through O, and the center of gravity is the center of the rod, which is a distance x away, so that will make it mgx. Okay, now what I'm going to do is, if you just skip towards the end of the question, I don't like square roots, never have, never will. Okay, so what I'm going to do is I'm going to square both sides. Okay, so when I square both sides, I'm going to get t squared equals 4 pi squared. The square root then is going to be m into L squared plus 3x squared all over 3mgx. Now, so whereas if we reread the question, it performs small oscillations. If it performs small oscillations, it obeys the compound formula rule, because it has to be small oscillations, because sine theta has to equal theta for the formula we just used. Find the value of x for which the periodic time is minimum. Minimum being the key word. Alright? Now, what we could do is we could do dt squared dx and put it equal to 0. Alright? And then prove that the second derivative, as in d2 d squared dx squared, equals 0. Okay? Now what I'm going to do is I'm going to highlight the variable part of the question. See this? See the parts underlined in purple? These are all constants. They don't change with differentiation. They're always going to be there. So what we can do is we can just leave them out. Okay? And just concentrate on the differentiable part. So what we're going to do, and I didn't do this in my notes by the way, so I need you to do it now. We're going to make up a different letter we haven't used yet. Call it capital K. Okay? Capital K is now represented by L squared plus 3x squared all over x. Okay? And what we're going to do is, K is basically the same thing as T squared, isn't it? Except it's missing a constant. So what we're going to do is we're going to get decay dx, which is going to be, and we're going to put equal to 0. Okay? So let's use the quotient rule, U and V. Quotient rule will turn out to be, what's it, phi times du dx? Yeah. So x times, differentiate the top, not differentiable, 6x. Then minus, differentiate v, we get 1 multiplied by u, L squared plus 3x squared. All over x squared. All equals 0. 6x squared minus L squared minus 3x squared all over x squared. Cross multiply that x squared, and what we're going to end up with is 3x squared minus L squared equals 0. Bring over L. Or sorry, we're going to get x on its own because we need to find the distance in terms of L. So bring L over. And then 3x squared equals L squared. X squared equals L squared over 3. And then x therefore is L divided by root 3. Okay? So, happy enough with that. Alright? Next step after this, I'll just make all this smaller for a minute. Okay. Now, my second derivative is located here. This here is my second derivative. Oh, sorry. My second derivative is actually 3x squared minus L squared all over. Sorry, my first derivative is that there. Everybody in agreement with that? Okay. Next thing I gotta do is get the second derivative and prove it's a minimum. Okay? So to get the second derivative, d2k dx squared. And what we're going to get here is we're going to differentiate it a second time. So we're going to have x squared multiplied by, what's that going to be, 6x. And then we're going to have minus 2x multiplied by 3x squared minus L squared. All divided by x squared to be squared, which is x to the power 4. Then once we have that done, we're going to get 6x cubed minus 6x cubed plus 2xl squared and over x cubed greater than 0. And what we're going to get here is 2l squared, oh sorry, x4, 2xl squared divided by x4 and greater than 0, and that's going to give me 2l squared over x cubed greater than 0. Now, this is always bigger than 0 because L is squared, length is positive and it's squared, and we're told that x is greater than 0 because x is a displacement away from the center, which is positive. Okay, so therefore it's always greater than 0. This makes it a minimum, which proves our question. Okay, that's it. So now, a uniform square ABCD, that's a circle, don't get that mixed up. Alright, ABCD. Now, ABCD, when you read this in any maths book, it usually means you're going anti-clockwise, okay? So A, B, C, D. And that's what I found in general. That used to confuse me, which way do I actually draw it, but any textbook or any solution I ever seen now seems to be always going anti-clockwise, okay? Now, has a side 2L and is free to rotate about a horizontal axis perpendicular to the plane of the lamina. That means it's, let me see if I can, like this, it's doing something like that. Okay, if I was to do it through its center, that's what I'd be doing, okay? And you can just imagine if I grabbed it by its corner, it'll be doing a different type of rotation, okay? Now, which is a distance x from the center of mass, side 2L. Now the side 2L is a good thing. Why is it a good thing? Because it's going to be exactly the same as the formula that's in your tables. There's no adjustment required. Mass m, once again saying no adjustment required from the formula that's in your tables. Axis perpendicular to the plane. That's something we got to look out for. The only formula we have for a lamina isn't perpendicular to the plane. It's horizontal to the plane, which means we're going to use the perpendicular axis theorem to convert it to perpendicular to the plane. Okay? Which is distance x from the center of mass of the lamina. Center of mass of the lamina, anybody? Dead center. Okay? It's got to be dead center. And you must draw, they're meant to intersect at that center of gravity point, but there we go. Okay, so that's our center of gravity right there. Okay, so we'll call it x and y. Oh no, not x. I have to use y and z now. Okay, because x is already taken. Okay. Along the diagonal, it's rotate through point P, and P is going to be located through point P, which is distance x from the center of mass along the diagonal AC. Okay, that doesn't necessarily mean that P is actually in the corner, does it? Nothing in the language to say it's in the corner, isn't that right? So all what we know is if we join a diagonal from A to C, like so, P is located somewhere on that line. So if you imagine, I'm actually rotating it through this point here, and it's bobbing around. Okay, so it's going around and it's going in this direction. Okay, it's rotating around, but it's being held by the point P. So
would it not extend
in a nutshell, look
up to the C?
Huh?
Would it not extend full out to the C?
It could, yeah, diagonal AC. But if I stop at the midpoint, it's still the diagonal AC.
Well, that's only if you follow it AC. If you follow it mid.
Oh yeah, but it just keeps continuing.
Right.
Because it's the same slope, so there's no worry about that. Okay, so prove that when the period of small oscillations is a minimum. Small oscillations means our formula for what's that? The 2 pi. Where is it? The 2 pi I over mgh is in play, which is brilliant because that's what we need to do. Okay, so let's go about doing this. For a IY, the moment of inertia about the y-axis when it's going through its center. Okay, there's a proof for that. It's a third ml squared. It's the second proof we did. IZ, which is another axis, remember they're all lengths L either side. That's also going to be a third ml squared. Now if I was rotating it around its center, okay, sorry, this here is this rotation. The third ml squared is this rotation here. We don't want that. we want it this way. We're going to have to do the perpendicular axis theorem. Perpendicular axis theorem. Okay. I'm going to call it IG. IG equals IY plus IZ. It's both added together. IG therefore is going to be 2/3 ml squared. Now, the problem is with IG is it's located in here, but P is located here. But now both of them are going in the same direction, and because they're going in the same direction, we can now use, this is the perpendicular axis theorem, and now we're going to use the parallel axis theorem. So the parallel axis theorem is basically going to be what are we doing here now? Yeah. Okay. IP equals and remember it's a distance x from the center of gravity. Okay, that's what we were told earlier. Okay, so it's going to be IP is going to be IG plus MD squared. Okay, that will give us 2/3 ml squared plus mx squared. Do what we did last time, put a 3 top and bottom and factorize, and what we can get is 1/3 m into 2l squared plus x squared. Okay. Once we've done that, I'll be back down in a second for you. Okay, sorry. There we go. Okay, that's our formula we're going to be using next. Okay.
Not 3x squared.
It is 3x squared. You're right. Sorry, 3x squared there. Now, what we're going to be doing next is we're going to start using this formula here. Okay. And when we start using this formula, what's going to happen is we're going to put it into the terms of the periodic time. Now, to put in terms of periodic time, we're going to do t equals 2 pi, our moment of inertia. Just have m on top, 2l squared on the bottom, 2l squared plus 3x squared. Put the 3 on the bottom. And then we have m, which is still m, g, which is still g, and h is going to be x. Now the reason why it's x, once again, h is defined as the distance from the center of gravity away from the axis we're talking about. Okay? So what we're going to get here, we're going to square both sides. And before we square both sides, we're going to cross off those m's because they can cancel. And what we're going to get is 4 pi squared, 2l squared plus 3x squared. And I'm going to put the g and the 3g outside. And I'm going to put the x in here. Now, once again, you can flick to the back now. We have a very much a differentiable part. The differentiable part is located here. Okay, here's the differentiable bit. Once again, I'm not to call it t squared because it's not t squared, it's part of t squared. And I'm going to call it k again. So this is equal to k. And the next thing I'm going to do, once I've done that, is I'm going to start differentiating it. Okay, so we're going to start differentiating it. So what we're going to get is dk dx ends up to be, remember u is going to be 2l squared plus 3x squared, and v is going to be x. So phi times du dx, x multiplied by 6x, minus u times the v dx. The v dx is 1, and the u dx is 6x. Oh wait, I wasn't meant to do the u dx there, I just want to keep it as 2l squared u. And then all on the bottom, we're going to have x squared. Then multiply it out. 6x squared minus 2l squared minus 3x squared, all divided by x squared. And what we should get here, 3x squared minus 2l squared, all of x squared equals 0. Once again, to solve that, you're going to get 3x squared equals 2l squared, and then you're going to get x equals l divided by root 2 over root 3. Sorry, root 2 over root 3 multiplied by l. Okay, second derivative test coming up. Prove that it's going to be a minimum. Okay, so what we're going to do is dk squared dx squared. Oh sorry, it's not dk squared, it's d2k sorry, d2k dx squared. Remember the 2 goes in between the letters. Differentiate. This time u is 3x squared minus 2l squared. V is x squared. So we're going to get x squared multiplied by 6x. We're going to get 2x multiplied by 3x squared minus 2l squared, all divided by x squared to be squared. Then we get 6x squared, x cubed, minus 6x cubed, plus 4xl squared, divided by x4. And like last time, we're going to get 4l squared over x cubed is greater than 0, because x is greater than 0, l greater than 0, minimum. Okay, a uniform square lamina ABCD. This one goes clockwise for some god unknown reason. Usually goes anti-clockwise, this time it's clockwise. But I think if you rotate that around, it still turns into ABCD. No, it doesn't. So, from what I've learned now is that you can do it any way you want once it's in order. That's always confusing you more than it should. A uniform square lamina of ABCD of mass 3m inside root 2 is free to rotate with its plane vertical through a point P on the diagonal AC. The point P is the distance x from the centre of mass of the lamina. A mass m is attached at each point A and C. Now, it's like the last question, except there's 2 masses attached here. First question I'm going to ask you is, does the placement of these 2 masses affect the centre of gravity of the system? Does the placement? No. Why not? They're on the same axis, and they're the same distance away from the centre of gravity. Centre of gravity is completely unaffected. Okay, that's the important thing to note. Okay. Now, let's begin. I'm going to make 2 axes. First axis here, I'm going to call it IY and IZ for me, because that's the way I like to do these ones. IY, IZ. Now, once again, remember. Oh wait, sorry, excuse me. No, those ones are wrong. Excuse me. When you're doing a lamina, the lamina has to be going dead through the side of the square, cutting it in half, L either side. So it's basically like the last question, except we're rotating it. Now, I'm now defining two axes. This is going to be y, this one's going to be z. Okay, I of y, by our first proof in the notes, is a third ml squared. But we got to check that out. That's for mass m, length 2l. What's the mass in this question? Mass 3m. Okay, so it's mass 3m. And what's the side lengths? So L equals root 2. Oh, sorry. The length is 2L. 2L equals root 2. This means that L equals root 2 over 2. Okay? Change this formula into a third. 3m. L squared is going to be root 2 over 2 squared. Okay? Multiply that out. And it gives you m over 2. By symmetry, IZ is the same thing because it's a square. Okay? Then, once again, these forms I use are for this type of rotation. We want this here. We need the perpendicular axis theorem. Okay? So the perpendicular axis theorem is going to be where we wrote IG because it's going through the center, right? So IG, which is an axis perpendicular to both of them, okay, is going to be it's going to be IY plus IZ, which is m over 2 plus m over 2, which is conveniently just equal to m. Okay? Now, let's use the perpendicular axis theorem because we don't want it going through G, we want it going through P. P is the target. Okay? So this is we just have to use the perpendicular axis theorem. Now we're on to the parallel axis theorem. And once I do the parallel axis theorem, what's going to happen is we're going to do IP equals IG, which is m, plus md squared. So it's going to be m plus, now remember this m is 3m and d is x. So it's going to be m plus 3mx squared. Okay? Also what we've done thus far is we've only done the square, the lamina. We haven't actually touched the, we haven't actually gone near the point masses yet. And that's what we need to be looking at as well, is the point masses, okay? So, okay, so we're going to be doing the point masses in a second, okay? So that's our IP for the, everything in the green, lamina. Now we're going to go to the point mass. And the point mass is done in red. Okay? So we're going to go for the point mass at A. Now the point mass of A, it's IP. Now, what is the distance of A from the axis P? Can anybody tell me? How to figure that out? Okay. Okay. If I was to draw a little triangle here, if I was to draw, I'm going to draw a big green triangle here. Right, ready? Everybody see that? The length, the hypotenuse is root 2. Okay? The other two sides are equal in length because they have to be, because it's a square. What two sides, when combined together, give you root 2? It's going to be 1 and 1. Because 1 squared plus 1 squared is 2. Square root of 2 is the hypotenuse by Pythagoras' theorem. So that means that from G to A is the length 1. So what does that mean from A to P? 1 minus x. Okay? So it's going to be, remember, point masses is md squared. And it's going to be m times 1 minus x squared. That's its rotation around A. Now for point mass B, its moment of inertia about P is going to be, it's down here. So it's a distance of 1 plus x away. So it's going to be m times 1 plus x squared. Okay? So that's our 2-point masses sorted. Next thing I'm going to have to do is I'm going to have to get I total. Okay? And I total is going to be my lamina plus my 2-point masses. Now my lamina is m plus 3mx squared. My point masses is m into 1 minus x squared, or 2b squared, plus n times 1 plus x 2b squared. Okay, just need to multiply all that out. Go and get is m plus 3mx squared plus m minus 2mx plus 2m x squared plus m plus 2mx. Oh, sorry, that's not 2mx. I made a mistake there. Just be very careful. It's just mx squared plus mx squared. That's getting a bit messy there. Okay, let's see what we can cancel off. The 2mx's are gone. We are going to have 3 m's underlined in black here. M, and M, 3 of them. And then we're going to have mx squared plus mx squared plus mx squared is going to be 5mx squared. That's our I total. Okay. And we're done for the first part. Prove that the moment of inertia of the system about a horizontal axis through P is 3 plus 5x squared. Show that if t is the period of small oscillations, then t squared equals 4 pi squared over 5g, 3 plus 5x squared over x. Okay, can do that. It says small oscillations. When it says small oscillations, this is the form that I'm going to use. Okay, then what I can do here is going to be 2 pi into the square root of I, which is 3m plus 5mx squared, divided by m. Oh, be careful about that. What's the weight of the system? The weight of the system, 5m, because it's 3m for the lamina and 2-point masses. So be careful, like it'd be really bad if you got that far and just through an oversight, you're rushing in the test, you're not thinking. Don't go on autopilot, keep thinking about what each letter means. 5mg. Now you're going to have to double check the h. Is hx in this one? Centre of gravity located here. Distance x from the axis we're talking about. Yes, it is. It's still x. Okay. Square both sides. Cancel the m's. And we get t squared equals 4 pi squared. Brackets. The 5g is there now. Popping out the bracket there. Then we're going to have 3 plus 5x squared all over x. Okay. Now that's done. What we're going to be looking at next is find the value of x which gives the minimum periodic time. Now, in a test, okay, what I'd be doing in your shoes is sometimes just get the x value, okay? And some of the marking schemes, it doesn't really come up about the second derivative. So if I was in your shoes and you were really stuck for time, do the first derivative, get the value of x, If you have 3 minutes at the end of your exam, go back, do the second derivative just to ensure the marks. You'll see the marking schemes. Okay, they sometimes don't include the second derivative, so it's a time dependent thing. Okay, I'll show you them in more detail later on in the year. Okay, this here is going to be called k. K equals 3 plus 5x squared all over x. U value is 3 plus 5x squared. V value is x. So we're going to get dk dx. What we're going to get is x times 10x minus 1 times 3 plus 5x squared all over x squared. Put it in, we're going to get 10x squared minus 3 plus 5 minus 5x squared. And we're going to get 5x squared minus 3. This should be at the back of your notes. All over x squared. And this here has to be greater than 0, doesn't it? So not equal to 0, it's the first derivative, sorry, excuse me. Now, we're then going to get, when we solve this, this cross multiplies up into nothing. Bring the 3 over to your side. We're going to get 5x squared equals 3. And then we're going to get x equals the square root of 3 over 5. Okay, that's the length we're looking for. Finally, what we're doing after this is we're going to do the second derivative. And the second derivative is going to be d2k dx squared. And this is u is going to be 5x squared minus 3. V equals x squared. Differentiate. X squared to be squared. V is going to be x squared times 10x. U is minus, oh yeah, sorry, it's going to be dv this time, so it's going to be 2x times u, which is going to be 5x squared minus 3. Now what usually happens is the x's will cancel off on top. 10x cubed minus 10x cubed plus 6x all over x4, and we want to prove it's greater than 0. And what we'll get here is 6 over x cubed greater than 0. This is true because x is greater than 0. This means it's a minimum. Okay.